This presentation describes and illustrates the basic principles of probability as applied to health data that are arrayed within a two-way classification table. A two-way table is formed by categorizing two variables, say variable 1 and variable 2, and then combining categories of each variable to form the cells of the table. We often wish to use such data to determine to what extent, if any, there is a relationship between the two variables. By way of introduction, consider this strange-looking figure shown here that describes a sample of 20 persons who have been interviewed about their smoking history and who have been examined for possible respiratory illness. From the figure, we can count 9 smokers. And we can count 5 persons with respiratory illness. We can also find 4 subjects who both smoke and have respiratory illness. Based on these data then, what is the proportion of smokers among the total sample of 20 subjects? Since there are 20 persons overall, 9 of whom are smokers, the proportion we seek is 9 over 20, or 0.45. What is the proportion of persons with respiratory illness among the total sample? Since 5 of the 20 persons have respiratory illness, the proportion we seek is 5 over 20, or 0.25. What then is the proportion of persons who both smoke and have respiratory illness among the total sample? Since 4 of the 20 persons in the sample both smoke and have respiratory illness, the proportion we seek here is 4 over 20, or 0.20. Note that we are considering two binary variables here, smoking status, yes or no, and respiratory illness status, yes or no. We thus describe the proportions for categories of each variable separately, and we also describe the proportion of combined categories. As we shall describe shortly, each of these proportions represent estimated probabilities if we consider our sample of 20 persons to be representative of a larger population of subjects. The 3 proportions we have computed for these data are by no means the only proportions that we could have considered. Moreover, we can conveniently consider other situations by representing the data in the form of a two-way classification table shown here. Notice that the value of 20 at the bottom lower right of the table gives the total sample size being considered. The cell frequencies 9, 5, and 4 now added to the table correspond to the numerator of the 3 proportions we have already computed. And the rest of the cell frequencies in the table can be computed by subtraction, thus giving the complete two-way classification table shown here. There are several other probabilities that we could estimate from this table. For instance, the estimated probability of not smoking is 11 over 20, or 0.55. The estimated probability of not having respiratory illness is 15 over 20, or 0.75. And the estimated probability of not smoking but having respiratory illness is 1 over 20, or 0.05. A two-way classification table such as shown here allows us to address the general question of whether or not two variables are related to one another. Thus, in our example, we can use these data to determine whether or not there is evidence of a relationship between smoking and respiratory illness, or stated another way, whether knowing one's smoking status can predict respiratory illness status. We will address this general question in this presentation by way of another example. In this presentation, we have two objectives. First, you will learn to translate questions about health data in a two-way table into probability statements, and then to calculate these probabilities. Second, you will learn how to evaluate whether two variables in the table are independent. And here is a second example of a two-way classification table involving 297 subjects. The two variables here are weight and ulcer evidence. Weight is classified into three categories: underweight, normal weight, and overweight. Ulcer evidence is also classified into three categories: no ulcer evidence, nocturnal vomiting, and X-ray evidence. The three categories for each variable are mutually exclusive. That is, a study subject can be in one and only one category on either variable. Note that although a subject who has X-ray evidence may also have evidence of nocturnal vomiting, such a subject would nevertheless be classified in the more severe of the two conditions, namely X-ray evidence. The numbers in the table represent frequencies that count the number of subjects in various categories of either variable or a combination of categories of both variables. To describe the information provided by this table, we define an event to be any subset of the possible outcomes corresponding to one or more of the cells in the table. We now describe three types of events. First, a marginal event describes outcomes that are shown on either of the two marginals of the table. For example, here we show the marginal event of having X-ray evidence, noting that there are 47 subjects in the data set who have X-ray evidence, and that this number 47 can be found in the set of numbers located within the bottom marginal of the table corresponding to the X-ray evidence column. A second type of event is called an intersection event. Here we see that 22 subjects have both X-ray evidence and normal weight. Thus, this event represents the intersection of the row of normal weight and the column for X-ray evidence. A third type of event is called a union event, which represents the joining together or union of two or more events. Here we have formed the union of nocturnal vomiting evidence and X-ray evidence, which are two separate categories of ulcer evidence. The union of these two categories involves 150 plus 47, or 197 persons who have either nocturnal vomiting or X-ray evidence. Note again that someone with both nocturnal vomiting and X-ray evidence would be classified as having the more severe symptom, namely X-ray evidence. Here we clearly illustrate two mutually exclusive events: no ulcer evidence and X-ray evidence. These two events have no outcome in common, as is required for any two categories of each of the variables being considered in any two-way classification table. We are now ready to describe how to determine the probabilities that we can estimate from a two-way classification table. Such probabilities can be estimated using what is called the relative frequency definition of probability, which we now address. Note that the reason why we are using the term estimated probabilities is because we are assuming that we have a sample of data rather than the entire population from which the sample was drawn. We will use our two-way classification table relating weight to ulcer evidence to illustrate the relative frequency definition of probability. Let V denote any event of interest, and P of V denote the probability of this event. Then, using the relative frequency definition of probability, we say that P of V is approximated by N sub V divided by N, where N sub V denotes the number of subjects experiencing event V, and N denotes the total number of subjects in the sample. Alternatively, we can say that P hat of V equals N sum V over N is an estimate of P of V. So, based on the relative frequency definition of probability and the data, what is the probability that a randomly selected person from the study population will have no ulcer evidence? The question asks us to determine the probability of the event D having no ulcer evidence. Thus, P of D is estimated to be N sub D over N, that is, the number of subjects with no ulcer evidence divided by the total sample size. For our calculation, N sub D over N equals 100 divided by 297, which equals 0.337. This is a marginal probability because the calculation uses a marginal total. So now, what is the probability of having normal weight? This question again focuses on a marginal event. This time it's the event B of having normal weight. The probability P of B is therefore estimated to be N sub B over N, which is equal to 132 divided by 297, or 0.444. As a third question, what is the marginal probability of having X-ray evidence? We are now talking about the event F having X-ray evidence, so the probability of having the event F is approximately equal to N sub F over N, which is equal to 47 divided by 297, which is equal to 0.158. We will now talk about the probability of true and impossible events, and we will do this again in the context of our two-way classification table relating weight to ulcer evidence. The true event is an event that always has to happen. We sometimes refer to this as the universe and denote it by S. The probability of a true event is 1. In other words, P of S is equal to 1, always. The impossible event is an event that can never happen. We often refer to this as phi. The probability of an impossible event is 0, or in other words, P of phi is equal to 0, always. The probability of any event is equal to or greater than 0 and equal to or less than 1. In other words, 0 is less than or equal to P of V is less than or equal to 1 for any event V. So what is the probability that a person will either be under, over, or have normal weight? Well, the answer is the probability of A or B or C, which is equal to the probability of S, the universe, which is equal to 1. This is a true event. What is the probability of having no ulcer evidence or some ulcer evidence? This is the probability of D or E or F, which again is equal to the probability of the universe S or 1. This is also a true event. So what is the probability of having both nocturnal vomiting and X-ray evidence? Now this question is a little tricky, and you have to answer it based on the way the categorization of the table has been set up. The answer is P of E and F, which is equal to the probability of the impossible event, or 0. The reason why this is an impossible event is because we have defined the categories so that the events E and F are mutually exclusive. Well, here's an easier one. What is the probability of being overweight and underweight? The answer is P of C and A, which is the probability of an impossible event, which is 0. This is an impossible event because the events C and A are mutually exclusive. We now describe the probability of opposite events. We denote the opposite of the event V by the notation V bar. The probability of the opposite event V bar is 1 minus the probability of the event V. So P of V bar equals 1 minus P of V. So, what is the probability of having some evidence of ulcer? The probability of having some evidence of ulcer is the probability of D bar, which is 1 minus the probability of D, where the probability of D is the probability of having no ulcer evidence. So, to get our answer, we first find the probability P of D, which is approximately equal to N sub D over N, which equals 100 over 297, which equals 0.337, which rounds off to 0.34 to 2 decimal places. So, the probability of having some evidence of ulcer is 1 minus P of D, which is approximately equal to 1 minus 0.34, or 0.66. What is the probability of not having normal weight? This probability is the probability of B bar, which equals 1 minus the probability of B, where B is the event of having normal weight. P of B is approximately equal to N sub B over N, which is equal to 132 over 297, or 0.44 rounded to 2 decimal places. Therefore, P of B bar equals 1 minus P of B, which is approximately equal to 1 minus 0.44, or 0.56. For a third question about opposite events, what is the probability of not having X-ray evidence? Since F is the event of having X-ray evidence, F bar is the opposite event. So we want to get the probability of F bar, which is 1 minus the probability of F. So P of F is estimated as N sub F divided by N, which is 47 over 297, which equals 0.158, which rounds off to 0.16. And therefore, P of F bar equals 1 minus P of F, which is approximately equal to 1 minus 0.16, or 0.84. We are now ready to describe how to determine a cell probability. The cell probability is the probability of a joint or intersection event. If U and W are two events, the probability of U and W approximately equals the combined number in both U and W divided by the total number in the study. Or in other words, P of U and W equals the probability in the cell determined by the intersection of the two events U and W, which is approximately equal to N sub U and W divided by N. So what is the probability that a person will have X-ray evidence of ulcer and normal weight? The answer is the probability of B and F, where B is the event of having normal weight and F is the event of having X-ray evidence. This probability is estimated by the number in B and F divided by N. That is, the number of subjects in the cell that combines B and F divided by the total sample size. Since there are 22 people in the cell that combines the events B and F, our answer for this probability is 22 divided by 297, which equals 0.074. For a second question, what is the probability of being overweight and having no ulcer evidence? The answer is the probability of the cell that combines the events C and D, which is approximately equal to N sub C and D, which turns out to be 35, divided by N, the total sample size. This probability is computed as 35 divided by 297, which equals 0.118. As a third question, what is the probability of being underweight and having X-ray evidence? The answer is the probability of the cell that combines the events A and E, which is approximately equal to the number in A and E divided by N. Since there are 5 persons in the cell obtained by the intersection of the events A and E, the answer is calculated to be 5 divided by 297, which equals 0.017. We now describe how to determine a combined cell probability, which is the probability of a union or additive event. It's defined as follows. If U and W are any two events, the probability of U or W equals the probability of U plus the probability of W minus the probability of U and W. Or in other words, P of U or W equals P of U plus P of W minus P of U and W. However, if U and W are mutually exclusive, then the probability of U or W equals P of U plus P of W. Question 1. What is the probability of having either normal weight or no evidence of ulcer? Our answer is that we want to find the probability of B or D, which by our formula is equal to P of B plus P of D minus P of B and D. P of B is 132 over 297. P of D is 100 over 297, and P of B and D is 45 over 297. This combines together to be 187 over 297, which equals 0.630. Question 2. What is the probability of being either normal weight or overweight? The question concerns mutually exclusive events C and B, so the answer P of C or B is equal to P of C plus P of B. P of C is 107 divided by 297, and P of B is 132 divided by 297. Combining them, we get 239 over 297, which equals 0.805. For our third question, what is the probability of being over or underweight? Here we are talking about the mutually exclusive events C and A. So the probability we seek is P of C or A, which is equal to the sum P of C plus P of A. P of C is 107 divided by 297. P of A is 58 over 297. Combining this, we get 165 over 297, which turns out to be 0.556. The last basic probability term that we now consider is the conditional probability, which is defined as the probability of an event V given the occurrence of another event W. We denote this by P of V given W, where the vertical line here denotes given or conditional on. P of V given W can be computed in one of two ways, either as N sub V and W divided by N sub W, or as P of V and W divided by P of W. Given this definition of conditional probability, we now ask, what is the probability that a person will have X-ray evidence given that he is overweight? This is the probability of having the event F, having X-ray evidence, given the event C, being overweight. You will notice in the table that there are 20 people who are both overweight and have X-ray evidence. So the formula P of F given C is approximately equal to the number of people who are both overweight and have X-ray evidence, which is 20, divided by the number of people who are overweight, or N sub C, which is 107. This calculation yields 20 divided by 107, which is 0.187. Thus, 18.7% of the 107 overweight persons also have X-ray evidence. We could have alternatively computed this conditional probability using the formula P of F and C divided by P of C. P of F and C is estimated by 20 over 297. P of C is estimated by 107 divided by 297. When we divide 20 over 297 by 107 over 297, we again obtain the answer, 20 over 107, which is 0.187. As a second question, we now ask, what is the probability of being overweight or normal weight given there is no ulcer evidence? This probability is the probability of the event B or the event C, the union of these two events, given the event D having no ulcer evidence. Looking at the table, we see that of the 100 people with no ulcer evidence, 45 plus 35 of these people have either normal weight or are overweight. So the formula is N sub B or C and D divided by N sub D. Computing this probability, we get 45 plus 35 divided by 100, which equals 80 over 100, or 0.80. For a third question, we ask, among overweight persons, what is the probability of having some evidence of ulcer? The answer is the probability of the event E or the event F, the union of these two events, given the event C, the event of being overweight. Looking at the table, we see that among the 107 persons who are overweight, 52 plus 20 persons have some evidence of ulcer. So the formula P of E or F given C is approximately equal to N sub E or F and C divided by N sub C. Calculating this conditional probability, we get 52 plus 20 divided by 107, which gives 0.673. Thus, 67.3% of the 107 overweight persons in the study also have some evidence of ulcer. This would be a good time for you to consider taking a short break. To do so, you should press the ESC or escape button on the top left of your keyboard, since this will stop running this PowerPoint presentation until you are ready to return for the second part. When you are ready to resume the presentation, please make sure to get back on the presentation to this screen with the break sign, then move to the next screen which says break is over, and finally click on the hourglass button at the bottom of the presentation screen to start the program running again. Okay, the break is over. We are now ready to describe how to determine whether two events are independent, leading us eventually to describe how to determine whether two variables are independent. We are now going to discuss the probability of independent events. We say two events V and W are independent if and only if the probability of V and W is equal to the probability of V times the probability of W. In other words, the probability of the intersection of two events is equal to the separate probability of each event. So to decide whether two events are independent, we must do the following. First, we compute P of V and W, the observed cell probability. Second, we compute P of V and P of W, the marginal probabilities. Third, we compute the product P of V times P of W, which is called the expected cell probability. And then lastly, we compare P of V and W with the product P of V times P of W. Based on this definition of independent events, we now ask, what is the expected probability of being overweight and having some ulcer evidence if these two events are independent? If the events C, being overweight, and the event E or F, having some ulcer evidence, are independent, then the probability of C and E or F is equal to the probability of C times the probability of E or F. Calculating this probability, we get P of C is estimated to be 107 over 297, and P of E or F is estimated to be 150 plus 47 over 297, and multiplying these two estimates together, we get 0.238. Having now determined the expected probability of being overweight and having some ulcer evidence, we now wish to know what is the observed probability of being overweight and having some ulcer evidence. This probability is the intersection of two events, the event C being overweight and the event E or F having some evidence of ulcer. This is a cell probability, and the formula is P of C and E or F. Calculating this probability, we get 52 plus 20 divided by 297, which is 0.242. So how do these observed and expected probabilities compare? 0.238, the expected cell probability, and 0.242, the observed cell probability. Comparing the observed and expected cell probabilities, we find that these two are very close, which indicates that the two events, being overweight and having some ulcer evidence, are independent events. For another question we now ask, are X-ray evidence and normal weight independent events? To answer this question, we first compute the estimated cell probability, which is the probability of the intersection of the events B having normal weight and the event F having X-ray evidence. And this probability is estimated to be 22 divided by 297, which is 0.074. This is the observed cell probability estimate. For step 2 in this process, we compute the separate marginal probabilities P of F and P of B. P of F is equal to 47 divided by 297, and P of B is equal to 132 over 297. So P of F is 0.15 and P of B is 0.44. Multiplying P of F and P of B, we get 0.15 times 0.44 is equal to 0.066. This is our expected cell probability. Comparing the observed cell probability of 0.074 with the expected cell probability of 0.066, we find that these two probabilities are quite similar, and therefore we will conclude that the two events of having X-ray evidence and having normal weight are independent events. Having now shown how to compute both observed and expected cell probabilities, we are now ready to construct a probability table for the entire data. So, corresponding to the two-way table of observed frequencies involving numbers of people, we can construct a two-way table of probabilities, where we have observed numbers in the cells and marginals of the frequency table. We can put in correspondence observed probabilities in the cells and marginals of the probability table. We can also put in the probability table, in parentheses, expected cell probabilities assuming independent events. So based on the information we've provided, what is the observed number, observed probability, and expected probability for people who have normal weight and no ulcer evidence? The observed number of people who have normal weight and no ulcer evidence can be found in the top table of cell frequencies, and that number is 45. The observed cell probability of B and D is found in the bottom table, and that's computed to be 45 over 297, or 0.152. The expected cell probability of B and D is given by the product of the two marginal probabilities, 132 over 297 and 100 over 297, which equals 0.150, which is also shown in the bottom table of probabilities. As another question, this time dealing with the marginals of the table, what is the observed number and observed probability for people with no ulcer evidence? This is a marginal event. The observed number of people with no ulcer evidence is found in the top table, and the answer is n sub d equals 100. The observed probability for people with no ulcer evidence, which is a marginal event, is equal to 100 over 297, which equals 0.34, and can be found in the marginal of the probability table shown at the bottom. The probability table shown below for the weight and ulcer evidence data has now been completely filled in with both the observed and the expected cell probabilities as shown in the middle of this table. We have just finished talking about the independence of two events in a 2x2 classification table. We are now ready to start talking about the independence of two variables in such a table. We define two variables to be independent if each event for one variable is independent of each event for the other variable. In other words, if for each cell of the probability table, the observed cell probability is more or less equal to the corresponding expected cell probability, then the variables are independent. Thus, to evaluate whether two variables are independent requires an overall evaluation of whether the events for each cell are independent. So for these data, are the variables weight and ulcer evidence independent? We would conclude yes, because for almost all cells in the table, the observed and the expected probabilities are quite close. There are exceptions. Cells corresponding to the intersection of the events A and F give an observed probability of 0.17 and an expected probability of 0.031, which are somewhat different. And the cell corresponding to the intersection of C and F gives an observed cell probability of 0.067 compared to an expected cell probability of 0.057, which is also somewhat different. We have completely filled in the bottom probability table with the observed and expected cell frequencies. What about the top table, which now only shows observed cell frequencies? To complete the table, we will need to compute expected cell frequencies, which we now describe. Moreover, expected cell frequencies in a two-way table are very important because they are needed for the computation of a single index called the chi-square statistic, which is used to determine whether two variables are independent. The expected frequency in a given cell is defined to be the number of observations that would be expected if the two variables were independent. The expected cell frequency is obtained by multiplying the expected probability by the total number of people in the study. Thus, E equals N times the expected probability. So what is the expected frequency for people with normal weight and no ulcer evidence? From our formula, this expected cell frequency is equal to 297 times 0.150, which equals 44.6. So how does the expected frequency compare with the corresponding observed cell frequency? The expected cell frequency is 44.6. The observed cell frequency is 45. These are close. Using our formula for the expected cell frequency, we are now able to fill in the entire top table of cell frequencies with both the observed and the expected cell frequencies. We are now ready to introduce the chi-square statistic. The The chi-square statistic is a single index used to determine whether two variables are independent. Chi-square is determined as follows. First, compute the observed minus expected quantity squared divided by the expected for each cell in the frequency table, where O equals the observed number in the cell and E equals the expected number in the cell. Second, add the O minus E square over E values for all the cells in the table to get the chi-square statistic. If the chi-square statistic is considered small, we conclude independence. If the chi-square statistic is large, we conclude dependence. So, based on the formula for the chi-square statistic that we have just described, and on the data relating the variables weight and ulcer evidence, can we now say that weight and ulcer evidence are independent variables? To answer this question, we must use the cell frequencies in the table at the top to compute a chi-square statistic, which is the sum of 9 values of the form O minus E square over E. The first of these values, which corresponds to those subjects who are underweight and have no ulcer evidence, is given by 20 minus 19.6 quantity squared divided by 19.6. The second of these values, which corresponds to those subjects who are underweight and have nocturnal vomiting evidence of ulcer, would be given by 33 minus 29.4 quantity squared divided by 29.4. And the last of these 9 values would correspond to those subjects who are overweight and have X-ray evidence, and that would be given by 20 minus 16.9 quantity squared divided by 16.9. When we add up all 9 values of O minus E square over E, we obtain the chi-square statistic 3.17. This chi-square value of 3.17 would be considered small by statisticians. Therefore, we would conclude independence. You may wonder, how did we decide that 3.17 is considered small? Or more generally, how small is small? Or how large is large? The answer requires an understanding of statistical inference, which is beyond the scope of this presentation. Although we can always use a chi-square statistic to quantify whether two variables are independent, it is also possible to eyeball the data to assess independence qualitatively. Here we show two 2x2 two-way classification tables, one of which shows independent variables and the other which shows two variables that are not independent. Can you tell which one of these indicates independence and which one does not? The table at the top left indicates two variables that are not independent. We can eyeball these data by drawing horizontal arrows to compare how the data in one column changes to the other column for each row of the table. For the top table, in row B, the cell frequency decreases from 45 to 5, so we have drawn a downward arrow. In contrast, in row B bar, representing the other category of B, the cell frequency increases from 5 to 45, so we draw an arrow upward. When two such arrows go in opposite directions, or more specifically are not parallel, we can conclude that the two variables being considered are not independent. The table at the bottom right, on the other hand, indicates two variables that are independent. Once again, we can eyeball these data by drawing horizontal arrows to compare how the data in one column changes to the other column for each row of the table. This time, for the table at the bottom right in row B, the cell frequency decreases from 45 to 5, so we have drawn a downward arrow. Also in row B bar, the cell frequency decreases exactly the same way, from 45 to 5, giving the same downward arrow. When two such arrows go in similar directions, or more specifically are parallel, we conclude that the two variables being considered are independent. Alternatively, we can eyeball independence by drawing vertical arrows to compare how the data in one row changes to the other row for each column of the table. Thus, in column A at the top, the cell frequency decreases from 45 to 5, so we have drawn a vertical arrow that leans downward to the left. In contrast, in column A bar, representing the other category of A, the cell frequency increases from 5 to 45, so we draw a vertical arrow that leans to the right. Again, when two such arrows go in opposite directions, or more specifically are not parallel, we can conclude that the two variables being considered are not independent. Similarly, we can eyeball independence for the bottom right table by drawing vertical arrows to compare how the data in one row changes to the other row for each column of the table. Thus, in column A at the top, the cell frequency remains the same at 45 in each row, so we have drawn a straight vertical arrow to indicate no change. Similarly, in column A bar of the bottom right table, the cell frequency stays the same at 5 when going from one row to the other, so we again draw a straight vertical arrow to indicate no change. Since both these straight line arrows go in the same direction, or more specifically are parallel, we can conclude that the two variables being considered are independent. We now use a second example to consider how to eyeball whether or not two variables are independent, this time involving 4 different 3x3 classification tables. Using our eyeballing procedure, we will see that both the table at the top and the table on the left indicate two variables that are not independent. Also, by eyeballing, we will see that both the table at the right and the table on the bottom indicate two variables that are independent. For the table at the left, we can see that the horizontal arrows corresponding to each row of the table are not parallel, thus indicating non-independence. On the other hand, if we drew vertical arrows on the table at the left, we would also see that they are not parallel, also indicating that the two variables are not independent. So whether we draw our arrows horizontally or vertically, we arrive at the same conclusion that the two variables in the table at the left are not independent. If we now turn to the table at the top, we can see that the horizontal arrows corresponding to each row of the table are not parallel, thus indicating non-independence. If alternatively we drew vertical arrows on the table at the top, we would also see that they are not parallel, also indicating that the two variables are not independent. So whether we draw our arrows horizontally or vertically, we arrive at the same conclusion that the two variables in the table at the top are not independent. Now let's look at the table on the right. Here we can see that the horizontal arrows corresponding to each row of the table are parallel, thus indicating that the two variables here are independent. If alternatively we drew vertical arrows on the table at the right, we would also see that they are parallel, indicating that the two variables are independent. So once again, whether we draw our arrows horizontally or vertically, we arrive at the same conclusion, that the two variables in the table on the right are independent. Finally, we look at the table at the bottom. We can see that the horizontal arrows corresponding to each row of the table are parallel, thus indicating that the two variables here are independent. If alternatively we drew vertical arrows on the table at the bottom, we would also see that they are parallel, indicating that the two variables are independent. So whether we draw our arrows horizontally or vertically, we arrive at the same conclusion that the two variables in the table at the bottom are independent. We have now completed how to eyeball independence in a two-way classification table. This concludes this presentation on probability rules in the context of two-way classification tables. We suggest you use the viewing study guide that accompanies this presentation to review what we have covered, and then work the practice problem that is provided. To introduce the practice problem here, we provide a two-way classification table derived from a 1955 study by S.J. Liao in Public Health Reports on responses to smallpox vaccination in military recruits made during April and June 1951. In this study, subjects were vaccinated at processing centers before arrival at training camp. Vaccine responses were read twice and classified as primary, accelerated, and immune. Only the primary reactions were considered to be an indication of lack of specific immunity. The table shown below presents data describing the relationship between the time since previous smallpox vaccination and response to present vaccination. Based on this two-way classification table, you will be asked several questions that involve the probability rules described in the presentation, as well as questions on how to assess whether or not the two variables, time since previous vaccination and response to present vaccination, are independent.